Okay, so we'll take up with the plate cutting processes, because as we have seen in the entire ship construction or shipbuilding sequence of activities, after your plate preparation, then you have to cut the plates to the required size. The plates, they come in standard sizes. We have talked about it, just repeating it once again. They are generally of this size, that means 10 meter by 2 meter or 10 meter by 3 meters. They are the standard dimensions, standard sizes. There are rolling mills who also produce 10 meter by 2.5 meter, that is also there, but most popularly 10 by 2 or 10 by 3 in different thicknesses. They are available, various thicknesses. The thickness variation could be of the at 0.5 millimeter interval to a certain thickness, then could be 1 millimeter interval, then could be 2, 5, different. So, you have plates of say 4 millimeter as well as you have plates of 80 millimeter, different depending on your requirement. You can get your plates. So, you get them flat, straight, flat and of the standard size. Depending on your requirement, you have to cut it. That cut plate can be anything. That means within this you have the plate. So, in fact, the operation needed is that once the sizes and dimensions and the shape of the cut plates are established, then you have to put those things within this standard size of plates, right. That means, you have to mark them, do the necessary marking, or you have to draw it, whatever. Suppose your requirement is say 1, 2, 3, 4, there are the 4 typical shape are needed. Just arbitrary example I am giving. So, once you have that, once you know this size and the shape of this 1, 2, 3, 4, the flat 2 dimensional shape, then they need to be fitted on standard size of plates. I say fitted means, if I put them in a different fashion, I will say, I may see that I can only fit 3 of them, not all 4. Again, I change that sort of orientations, then I may find I am fitting not only 4, plus also I am having some plate where I can fit in some 5th component also, right. That means, there is some optimum way of fitting them. This particular aspect is referred to as nesting. This process of fitting the different shapes which needs to be cut out from a 2-dimensional plate, right. It is called nesting. Now, with the help of your computer and available softwares, these operations have become very easy. Means, you know the shape of all these. This you know from once you have the design done and the structural design also done. So, you know what all kinds of pieces are needed, right. You have seen in our structural arrangement various sizes of brackets, various types of floors, shell plates, everything is needed. So, once you have that, then you can do this so called nesting, such that you can make a utilization of the plate as much as possible, because you know the way I have drawn here, this part will remain as a so called scrap, is not it. This shaded part, what we are putting it, this is becoming scrap, means will not be used for anything, it will be thrown out, right. But objective should be to minimize this scrap, because there is a wastage. Okay. Anyway, So, that is what is nesting. Now, what happens once the nesting is done, then you need not now physically draw this on a plate, because we can have a cutting machine which is numerically controlled. Means once this diagram is known, then the computer can drive the cutting tool as per this diagram. So, automatically your plate cutting is done. So, you need not make any drawing as such, but if you do not have a numerical control cutting machine, then obviously there is no other option other than you have to draw this physically, make punch mark and then cut by whatever means. So, once that is ready, then it comes to the cutting bay. I mean, that is ready means, well, this is a part of a design job essentially, right, that nesting business. Once that is those information are ready, so you take the plate to the cutting bay, that digital information is there, it drives the numerical controlled cutting machine and it cuts it. Okay. So, now we come to the what are the cutting processes. Now, first thing what I have mentioned here is a mechanical process, and in mechanical process what we do is essentially shearing. The cutting is done by shearing. Schematically it can be shown in this fashion. That means, you have a stationary block, right, over which you keep the plate, and this is the cutting blade which moves vertically. This cutting blade moves vertically. So, you can imagine as if a cutting section like this, right. So, it is a cutting bed, right. That means, you have the bed and this is the bottom block over which you keep the plate, and this is your vertical blade which moves. It is like guillotine, something like guillotine you have heard in olden days, people used to, well, cutting something else, but here it is also referred to as guillotine shear. It cuts by shearing action. So, you can see this particular location where the shearing action will take place. That means, if I just draw it in a little enlarged fashion, you have the plate here kept and the blade this is putting the force, right. So, what happens along this section, a shearing action will take place, right, a shearing stress will be developed. So, you apply enough force such that shearing force what is developed exceeds the limiting shearing stress, and the plate gets sheared, essentially cut. So, that is the simple technique. So, in this what are the parameters involved? I mean, which will control this cutting operation. Obviously, one is this force, the force which it can apply. For example, the shearing machines, they are essentially powered by they will be generally hydraulic machines, right, and powering is in the order of hundreds of tons. That kind of force it should have. That means, this force, the higher the force it can apply, thicker the plate it can cut, because then only it can generate the required shearing stress. What else? Another thing is this particular angle, either this angle or the angle here, it is one and the same, either of them, this angle, that is another important. Another thing is this gap, this particular gap, say R, the gap between the two blades. If I take this bottom one is as a blade, so gap between that, because depending on the thickness of the plate you will have to increase or decrease that gap, that R, that gap R has to be either increased or decreased. With a thicker plate you will have to increase it, thinner plate you will have to decrease it, right. So, these are the basic parameters which needs to be controlled, right, which needs to be controlled for getting a shearing, proper shearing action. Now, so that way what we see is that this process is very efficient as such, because by one stroke it can cut the whole length of the plate, by one stroke. As we have drawn here, say this is my isometric view. So, if the length of this bed is more than say 10 meters, just more than 10 meter, that means the whole 10-meter plate I can put one stroke, you get it cut, isn't it? That means the cutting operation is very fast. That is one big advantage. What are the other advantage? That is the cutting edge. You get a very high quality cut edge, because the when you are cutting by shearing you get a smooth cut surface. That is important, because that cut surface will be further aligned to some other plate for further fabrication, could be, maybe you will have to weld and all that. So, if the cut surface is smooth, then you get a better joint, you get a better weld. If the surface is very rough, uneven, then obviously your welding will not be also good. So, that is another advantage, that you get a very good cut surface, a smooth surface, right. Third advantage is that it being a so called cold process means no external heat is applied. So, there is no thermal effect taking place on the plate, there is no thermal effect. What could be the thermal effects? That is thermal ill effects, like it could add to distortion, it can distort the plate, it could change the metallurgical parameters, right, because of the thermal action. It can change the microstructure, thereby the your property at the cut edge will change, all right. So, those things are not there. So, there is no thermal effect, because thermal there is no heat involved in this. So, that way this is much advantageous, quite a efficient method, but it has a great drawback. The great drawback is, say this simple example what we have drawn, a very simple shapes which we are cutting. In fact, 1, 4 and 3 all are rectangles, only 2 is also a rectangle, only one edge is sniped. Even this simple shape you won't be able to cut in this machine, because here I only for this part 1 I only need to cut this much, right, and part 4 is little lesser in width than part 1. So, I cannot continue it, again I have to cut here, and so on and so forth. Not only that, in many of these cut pieces you will need to have some such thing also cut already in the machine, those scallops, and if there is a angle, all those scallops, the stiffeners are to be fitted, all kinds of scallops, various kinds of curved cut shapes are needed. So, that is not possible here. So, that way this mechanical cutting machine, though very efficient and gives a very good quality cut, does not effect thermally, adversely effect, there is no adverse thermal effects, but still its use is limited. Limited to what? Limited to cutting straight edges, because in the construction you may also need, or you generally require various rectangular pieces of various dimensions. Now, as we have already I have told you that our stiffening members, one of the stiffening member is flat bar, isn't it? one of the stiffening member is flat bar. Now, these flat bars, if it is a standard dimension, then they are available. Available means like your so called bulb section or angle section, as there some of them are available, the standard sections. But if it is a non-standard, some flat is needed, then this shearing machine is idle. Suppose some well 500 by 9,000 millimeter, such a rectangular strip is needed. So, you put a plate, right, get this 500 measured, and one stroke you have that plate. That is how. So, these shearing machines, I mean mechanical cutting, though it has limitations, but still we will find their usage in shipyards, because there are requirement for flats, straight edges which needs to be cut. So, they are preferable to cut in the shearing machines. You will have fixtures such that with the help of a crane you put the plate on the bed, on the cutting bed, adjust it, and with a stroke you get it cut. So, that is how you see that mechanical cutting, it is quite a convenient method, easy and fast method, but only disadvantage is that it can cut only straight edges, not the what you call curved or any other shapes. So, it is only limited to that. Now, for cutting curved shapes, what is to be done? That means, you will have to have a mechanism by which the cutting tool can be moved anywhere in any shape. It can trace out any shape, because here my cutting tool is rigid, it is a straight blade, right. So, such cutting tool will not work, you will have to have a cutting tool which can move around. So, there comes the cutting by means of thermal effects. One is thermal and another is, well, again a kind of mechanical cutting only, that is water jet, right. For all practical purpose, or if you really look at it, this water jet cutting is also a mechanical cutting. Only thing here, the cutting tool, we have replaced the rigid straight tool by a powerful jet of water. So, when I am impinging the plate with a powerful jet of water, in fact, I am generating that level of shearing stress locally. I am plastifying the material locally, and it is going in the fully plastic state and blowing it off. Basically, that is what is happening. And to assist that cutting process, this water may have with it some abrasive material. That means hard solid powders of, say, silicon carbide, similar such, which helps in abrasion, because it is a kind of a abrasion cutting, right. So, that is what is water jet cutting. We will not go in much detail of that. All I think just the idea of it, that here again, since it is a jet, so I can move the jet in any direction. So, thereby I can cut any shape. That means, if my nesting is like this or any complicated nesting, it can be cut with water jet. Anyway,
shearing cold work, it is a cold work process. So, sir, work hardening can also take place.
No, here what is happening? Yes, what you are saying is correct. Work hardening means, what I said is, it is a cold work, thereby I do not have the ill effect of hot work. That means, there is no heat involved in it, but since it is in fact by cold working only it is cutting, that means it is at the room temperature, we are applying a force, and it is attaining the required level of stress shear stress which is exceeding the critical stress, and thereby is affecting the cut. And in the process, the cut edge is obviously subjected to a stress level much beyond the elastic limit, much beyond the elastic limit. So, the cut edge may have a harder, I mean will have tensile strength more than the rest of the plate. That means, that part will be more harder, that is there, that work hardening will take place, because there if we see that stress strain curve, it will be quite above the yield point stress. So, that cut edge will be work hardened truly, yeah. But what is happening, that edge is work hardened, and now that edge will get fully fused, because all these cut edges invariably will be welded to something. None of this cut edge will remain free, there will be some free, like the lightening hole in case of a floor, I am cutting it. So, those edges are free, let it be free, and that is not also subjected to heavy stress levels. And whatever work hardening is taking place because of such cutting, that is also not of that level that it can cause any eventual, I mean loss of ductility taking place, such that the crack will form. Those chances are very less, because of the location where it is happening. And also here if we see this in mechanical shearing cutting, they are all straight edges we are cutting. So, it is in 99% cases, all these edges which have been cut will be subsequently welded to something for fabrication of some structural component. So, once they are welded, so whatever change it took place, work hardening took place because of welding, that effect is nullified. So, that way that problem is not there as such. I mean that is not of concern, we can say. Like in case of short blasting, it was a matter of concern, but here it is not so. Okay. So, anyway, that is how we see that one of the most widely used process is thermal process of cutting. Now, in the thermal process of cutting, we have primarily two types of cutting. One is through so called oxidation, and another is through fusion. In both the process of, in the mechanical cutting, it was purely mechanical by applying force such that you exceed the shearing stress. In thermal cutting, what I am doing? I am putting heat by which either I am burning it off, that is oxidation, it is basically burning, is not it? Combustion, ignition, that is essentially a process of oxidation, right. So, either through burning the plate or through melting the plate. Fusion means essentially I am melting it. So, tell me what methods are used for thermal cutting. You may know, you may have done some first year experiments. What? Oxyacetylene. We will come to oxy and lens cutting later. It is what? Oxyacetylene. Spelling I have written correctly, acetylene, I think so. Oxyacetylene, right. So, what is this oxyacetylene basically is? It is basically a more general name would be what? More general name of oxyacetylene, oxyfuel, isn't it? A more general name would be, it's a typical case of oxyfuel cutting. Oxyfuel, isn't it? Because this acetylene I can replace it with our LPG, liquid petroleum gas. I can replace it with hydrogen, replace it with propane, butane. All these are fuel. In oxyacetylene, acetylene is the fuel gas. that burns, acetylene burns, oxygen does not burn, is not it? So, you may recall when you ignite the oxyacetylene torch, you first open the acetylene knob, ignite that and then adjust the oxygen knob, right. So, essentially it is a process. This oxy fuel, here the most popularly used fuel for cutting steel is acetylene, right. So, it is a oxyacetylene flame is used for cutting the steel plates. So, what is done there? That falls in which category? It is a category of oxidation cutting or fission cutting. That means, it is cut by so called burning or it is cut by melting. It is burning. So, this is a case of oxidation cutting. That means, what happens in the process?
Metal becomes oxide.
Metal is converted to oxide, right, and thereby the molten oxide is thrown off. That is how you achieve a cut edge. That is how you achieve a cut edge. So, you will find in the process what is done is, first you will have to heat up the plate and then you put in excess oxygen, extra oxygen. Once, if you recall, if you have cut in the first year workshop practice, you will find that with the oxyacetylene flame, you heat the plate from where you want to cut. After a few seconds, then you press another lever in the cutting torch, and thereby you may have observed the sound changes, means more oxygen by pressing another lever. In fact, you are injecting additional oxygen in the flame, that is being used to burn the plate, to oxidize the plate, oxidize the material there, that hot material, and then you keep on moving it at a certain speed which is suitable for that thickness, etc. So, you keep moving it. So, in the process what happens? That is the exothermic reaction. So, additional heat is generated, plate is getting heated up, coming to the necessary temperature, relevant temperature, wherein with that additional oxygen it burns, means gets oxidized, and you will find a spray of things coming down, that is nothing but molten oxide is thrown off. So, metal is not melted, it is a molten oxide is thrown off. So, there we will see, if you see in a temperature scale, it is something like this. Say this is my melting temperature of steel. How much melting temperature approximately? Tell me, I mean
5,000 centigrade.
very dangerous figures you are saying. Okay, let me see. One says 5,000 degrees centigrade, another says very precise 4,500, 700. Tremendous variation. Something more. 1,600. What? Fahrenheit? Degree centigrade. What? 14. Okay, let us write 1,400. Anything else? Guess. No, definitely you won't take average. This is also another important thing. Should you suppose you are doing some experiment and you get such data, at one point you are getting 5,000, another point you are getting 1,400, again you are getting 700. What do you do with this data? If you have such a, you scrap the experiment and do it again basically. And while doing it now, if you have many more 5,000s or 4,800, 4,700, 5,200, then what you do? Scrap these data 700, 1,600, 1,400. For some reason they came wrong. Take all those and take average of that, right. Anyway, any more guess? 1,500, and that is the temperature as such. Approximate temperature is 1,500, 1,490 or so, right. 1500 degrees centigrade. 700 is for aluminium, it's rather 600. Anyway, so this is about 1500 degrees centigrade. This is the melting temperature of the metal of steel. This is the, here it is a melting temperature of the oxide. Of the oxide, that is around 1000 degrees centigrade. Right. So, that is what it is. That means, when you heat up the material, and the ignition temperature is somewhere here around, well, ignition I write, that is around 800 degrees centigrade. By ignition I mean at the point where I am injecting more oxygen. So, when the plate attains that around 800 degrees centigrade, I press that lever to put more oxygen. How do I know that it has attained 800 degrees centigrade? Turn red hot, reddish color, red hot, because steel has a peculiar property. I mean, by seeing the color you can make out what temperature it is. At different temperature it exhibits different color. So, it becomes red hot, that is around 800 plus. So, you put in more oxygen and it starts cutting, right. Basically, then the temperature has gone up to 1000, right, around 1000, and the molten oxide is being thrown off. So, metal is not melted at all, its melting temperature is much above 1500. So, that is how steel is cut, right. That is pure oxyacetylene cutting. Now, if you want to now say I want to cut a 6 millimeter plate and then I want to cut a 60 millimeter plate, what would be the difference? The fundamental difference would be in cutting speed to start with, or more basic could be that whether at all 60 millimeter I will be able to cut or not. That question may come. Let me assume for the time being that we can cut a 60 millimeter plate. Obviously, the speed of cutting here in 60 will be much less compared to 6, right. So, productivity would be less, that is understood. What else could be the effect? Now, here what happens, like in mechanical cutting we had, yeah, all those things will come. Immediate effect would be the quality of the cut edge, quality of the cut edge. In case of mechanical cutting, we had a very good quality of cut edge. In gas cutting, oxyacetylene cutting, your quality of cut edge will depend much on the speed of cutting. If you have to cut at a slower speed, your edge becomes more rough. That means, if you look at the cut edge, it will have some such marking, it will come, right. By this I wanted to show thicker plate, you need slower speed of cutting, because you will have to attain these temperature levels, you have to attain that temperature level. So, you will have to give more time for the heat to flow, right. So, in the process at one location you have to keep the torch for a longer period, or in other words the speed of movement should be slow, and once the speed of movement is slow, so it is moving, so it forms those, it is moving this way, so it will form like this, those they are called curve. This cut edge is called curve, it will have a not a very smooth curve, right. Cut edge, as the thickness increases, cut edge will not be good. So, what is the solution to that? Solution is only how to increase the speed of cutting, because that is needed not only from having a higher productivity, but also higher product quality. I want to have the cut edge better, and also at the same time, if the cutting speed is less, then more part of the plate gets heated up. There is more heat flows in the plate direction. More part of the plate gets heated up. More it gets heated up means there is more probability of thermal deformation, right. Well, so one of the solution is
Cut from both sides.
no, that we cannot do, that you increase the heat content of the gas mixture. Now, I can cut it faster provided I can attain these temperatures 800,000 degrees centigrade. If I can attain them faster, so I can move the torch faster, I can cut faster space. That means I have to use a heat source which will have more heat content, because oxyacetylene in that mixture, it's how much heat will generate, it is fixed by process of your chemical thermodynamics. You cannot increase that. So, you can only increase if you add some additional substance. So, that is one of the method is oxygen lens cutting. What is that oxygen lens cutting? You have heard about that, isn't it? I also don't know much, don't worry. Anyway, oxygen lens cutting, that is essentially you put in that iron powder. In the gas mixture, you have a mechanism of putting in iron powder in that. That iron powder burns, exothermic process, that generates sufficient heat. So, when you go beyond a certain thickness of steel plate, you use oxygen lens cutting, that is what is called oxygen lens cutting, using iron powder in that. So, thereby increase the heat output of the flame, right. Anyway, but for all practical purpose in shipbuilding, in shipbuilding industries where you are cutting, when you are encountering such very thick plates, either you go for oxygen lens cutting or go for some other technique, some other means, laser cutting or plasma cutting, right, that way. Otherwise, for all practical purpose, it is purely oxyacetylene cutting. So, in oxyacetylene cutting, this is what is the principle. That means, you burn the plate and throw off the molten oxide, right. Well, so tell me, this is a case of steel. Now, if it is aluminum, then what we will do? Because there is aluminum fabrication also, isn't it? So, can we cut aluminum with oxyacetylene flame? Obviously, in mechanical, both aluminum and steel can be cut without any difficulty. Now, this we are going for thermal cutting because we have the advantage of now guiding the torch, the heat source we are using. So, you can cut anything and you have much better your productivity also. So, aluminum, what do we do?
So we can't cut.
Why?
So oxide has a very high.
Yeah, in aluminum what is happening, you see in the same scale, if I see somehow here it will be the melting temperature of the oxide, right, and somewhere here it will be the melting temperature of the metal, right, and the difference is, what is the melting temperature of oxide, any idea?
21.
Yeah, of that order, it is of the order of say 2200 degrees centigrade, above 2000 degrees centigrade, right, whereas the melting temperature is hardly 600 degrees centigrade. So, what happens is, if you try to cut, immediately, as you know, aluminum, its exposed surface is nothing but oxide, alumina, right, Al2O3. That Al2O3 gives its that corrosion resistance, protects it from further so called corrosion, right, because Al2O3 is quite inert in nature. So, if you want to cut it by gas, what will happen? That layer will thicken up only, further Al2O3 will form, and as you can see, before we could reach 2200 degrees centigrade, much of the plate will attain more than 600 degrees centigrade. So, we will have a molten metal inside, molten metal inside, the outside will be solid, thick crust sort of alumina, and inside metal will be in molten state. Or in other words, what will happen to the plate? Plate will just crumble. You have the plate, you move the torch, the plate will just crumble. I mean, it will sag and it will get totally deformed. Right? Why is deforming? Because it's losing all its strength. Inside the metal is flowing, it's in liquid state. Right? So, aluminum it cannot cut by oxidation gas. So, how do you then build the superstructure of aluminum? Because you will have to cut it. Aluminum also it comes in, well, not in 10 meter by 2 meter, but in a much smaller size. I do not recall exactly how much, but in a much smaller size, that is there. Whatever, it also comes in flat rectangular plates of different thicknesses. So, how do you cut it then?
Aluminum can be bent in.
But you need to cut a huge amount. I mean, that way it is not effective. And also again the same thing, if you have to cut a curved shape, all kinds, then how do you cut? Well, one is mechanical cutting, obviously is possible, but for curved shapes, how do we cut? There we go for cutting by melting, because there we will have to, well, I mean, the question of here, in case of steel, we could ignite the steel, we could burn it, right, and the melting temperature of the oxide was much less, whereas here the melting temperature of oxide is much high. So, I cannot afford to cut it by so called process of burning, oxidation. So, I will have to go by melting process, means I will not care whether the metal is melting or not, my objective is to melt the oxide straight away in aluminum. I need to have a much higher heat source, because as you can see, for steel I have to attain minimum 1500 degrees centigrade, for aluminum I have to attain 2000 plus degrees centigrade, right. So, that is what is cutting by fusion, and the method applied is, one of the method is plasma, by using a plasma cutting, or it can be laser cutting. That means, use plasma as the heat source or a laser beam as the heat source, and it can be cut. The whole point is, in both of them, they are very high heat input process. That means, momentarily you can attain a very high temperature locally. That means, very concentrated heat source. So, what happens is, you can attain the required temperature immediately, and that plasma jet or the laser beam will have enough force to throw up the molten metal. So, the metal gets melted and it keeps moving. So, if I can momentarily generate say 3000 degrees centigrade, so aluminum will be immediately cut. I am not allowing the heat to remain in position for a long time, such that heat gets conducted and the plate, the adjacent plate gets melted, right. So, that is how aluminum can be cut either by a plasma source or a laser source. Now, what is this plasma source? Well, maybe we can, what is that essentially? It is essentially, it is a, well, let us see schematically. Say this is a nozzle, right, and here you have an electrode, you have a power source, power source connected to this. Just schematically it is. So, here you put in a inert gas. If you know a TIG, tungsten inert gas welding process, right, it has some similarity in that. Here what we will have is some similar kind of a nozzle, right. Obviously, not exactly that of TIG, but similar thing. There also we gave a inert gas for shielding the welding material. So, here I am giving inert gas, you have a electrode, a non-consumable electrode, right, and a power source. Here I have drawn two power sources, here is one, here is another. What is the purpose of this smaller one is, here I have shown with a switch, means it is only used to ignite the so called flame, means it is a high frequency generator which initiate the arcing between the electrode and the nozzle body. In that arc, this inert gas will get ionized, right. The moment the ionization takes place, this is that high frequency source is switched off and the normal source is switched on. So, thereby I attain a continuous plasma column, as if a plasma flame, as if a gas flame. In gas burner you have a gas flame, in a plasma torch I have a plasma column of plasma, right. So, that means it again behaves same as that of a gas burner, as a gas torch, right. Only difference is here the heat is generated by this column of plasma and it has a very high intense heat, right. So, that is how this when applied to the plate, I mean this plate is subjected to or exposed to this plasma column, immediately it will attain the required temperature and start cutting it. And here the gas is, inert gas is flown in at a certain rate and it passes through the nozzle. Nozzle is so designed that it constricts the arc to the required dimensions, means the arc is not spread out, the plasma column is not spread out, rather focused. So, what happens? It heats more in a confined area, even confined more than gas torch. So, in plasma cutting I can attain a very good cut edge. The quality of the cut edge can be achieved is very high quality, near equal quality that of mechanical cutting, and obviously since here the power, how much power it will have or how much heat it can generate depends on the power. That power can be varied with increasing the power of the power source, right. So, effectively it can cut any thickness of plate, that means much higher thickness of plate also with plasma torch you will be able to cut. So, thereby whether it is steel or aluminum or titanium or stainless steel, anything can be cut, both ferrous and non-ferrous materials of virtually any thickness can be cut with plasma torch. So, these days in better equipped shipyards you will have plasma cutting workstations, means well obviously this is more expensive than your gas cutting, because here the raw material used would be inert gas, it could be generally argon. So, that is a costly thing, right. Plus the whole setup and the equipment is much costlier compared to oxide steel, which is much more cheaper. So, thereby one will have to, well, with plasma cutting you will have very high productivity because of the high intense source of heat. You can use a very high speed cutting. Now, well, if your downstream activities are of not that high speed, then investing in this and having a very high productivity cutting process won't make much sense. That is a different issue, but otherwise it will give you very high productivity, as well as you have the advantage of cutting not only steel, but also of aluminum. Anything can be cut, right. So, that is the in simple words, that is the way the plasma cutting is done and the advantages of this. But still oxide cutting is well, still it is used heavily for the simple reason that its cost is much less, and at the same time, as I said, that the productivity needed, that depends on, one will have to work out productivity of each workstation depending on the overall productivity. Means at one place I have a very high efficiency work, the very next place I have a very low efficiency, then in fact I am in trouble, because here I will produce more and that will get stockpiled, that is what is called bottlenecking. It will form a kind of a bottleneck, right. And especially this particular section we are talking about plate cutting. So, what will happen? Lot of plates will be cut and will get dumped, right. So, the plate you need will lie right at the bottom, because that is the one you have cut first, and you have gone cutting, it is dumped. So, you cannot take it out physically, there are this kind of problem. So, that way your this intercutting process, in this case what is happening, as I said, you are basically melting the plate. Similarly, you replace this plasma torch by a laser torch, it is laser cutting. Now, well, laser, the principle is different, generating the laser beam. So, we are not going in that, neither we are going in the details of how the plasma and how to constrict the arc, etc., etc. Basic principle is this. That means, we as a end user, that same cutting station where we are using a oxide torch, that torch can be replaced by a plasma torch. Again, that can be replaced by a laser torch. Only thing, your powering devices will be different. In case of oxide you will have gas pipes coming in from the central supply. In case of plasma, you will have the cables coming in. In case of laser, also some kind of cable will come in, right. So, that is the only difference. That means, here in plasma or laser you have high heat source. In some shipyards people have started using laser, but that is in a very limited, because with laser you can still have higher productivity, even higher thicknesses can be cut, but the cost exponentially increases, very high cost. Well, so we will stop here. Next we will see a little bit about this steel cutting. Once again we will go back to that regarding what are the difficulties one faces in this cutting processes. Okay.